The second factor other than planarity and the parallel orbital is that the orbitals must not be all empty or all completely filled. That is, we must have the emptiness for the electrons to travel and the electrons to travel. In fact, there should be alternate emptiness and the electrons for the conjugation to take place. Considering these two conditions can be satisfied actually in six situations. Now let's talk about those six such situations in which conjugation can take place. That is, these two conditions may be satisfied. The situations are the first one. We can have the emptiness and the electron. Now, when we talk about emptiness, emptiness actually is in three situations. When we talk about the situation for emptiness, that is the presence of the empty orbital. Empty orbital quite obviously turns out to be the emptiness. The second situation could be the presence of unpaired electron. Unpaired electron has one electron in an orbital that is counted as an emptiness. That is, we have unpaired electron, empty orbital. And then we have the pi bond. Now, pi bond is a peculiar thing wherein it is counted as an emptiness as well as the filled orbital. Because when we talk about the pi bond, let's say we have the pi bond between the two carbons, this pi bond is made up of the overlap of two p orbitals, two unhybridized p orbitals. The capacity of 2p orbital is 4 electrons, but there are 2 electrons which are present. So if we consider the bond to be cleaved, the heterolysis of the pi bond, this would lead to the formation of an empty orbital on one carbon and an electron pair on the other carbon. So that is how the pi bond behaves as an emptiness as well as the electron. So these are the three conditions which could be emptiness. Then we could have the electrons. The electrons can be provided by two species. One, lone pair. That is, we have two electrons in the same orbital, or the pi bond. As I have already told you that pi bond behaves as an emptiness as well as electron pair. So considering these five things, that is, we have the three situations talking about the emptiness and two situations talking about the presence of the electron pair, there could be six combinations which give us the conditions satisfying conjugation. So let's talk about the combinations. The combinations could be the first one, pi, single bond, pi. That is alternate pi bond. The example could be CH2, double bond CH, single bond CH, double bond CH2. That is a conjugated diene. Even benzene falls under this category of combination. Then we could have the pi bond single bond with a lone pair. That is, we have alternate pi bond and the lone pair. The lone pair provides us the electron and the pi bond gives us the emptiness. So the example could be CH2, double bond CH, single bond Cl, and there could be something like benzene ring having chlorine attached to it. Chlorobenzene satisfies this condition. The third condition could be the pi bond, single bond, and the empty orbital. This could be satisfied by the allyl carbocation. The allyl carbocation CH2 positive, or we can even have the benzyl carbocation. Please understand the allyl and benzyl carbocation are stabilized by conjugation, wherein the positive charge is distributed over multiple carbons due to the conjugation taking place here. The fourth case could be that we have a pi bond, we have a single bond, and we have an unpaired electron. Here comes the allyl radical. The allyl radical has carbon with an unpaired electron which can conjugate with the pi bond. Similarly, we have the benzyl radical. Benzyl radical has again the unpaired electron on a carbon attached to the benzene ring, which can be conjugated. The allyl and benzyl radical again are satisfied or stabilized by conjugation. Then we could have the lone pair, a single bond, and an empty orbital. Now, this is a peculiar case that can be satisfied with the organic compound as well, but we could have certain inorganic compounds satisfying this condition. Something like we have H2N, BH, NH, BH2. Now, this particular compound is called a borazide. Borazide contains nitrogen with the electron pair, while boron is there with the empty orbital. So it is having a lone pair, single bond, empty orbital, and that is what we have as the sequence. We could have it in the cyclic structure as well, like we have BH, NH, NH, BH, BH, and NH. Now, this particular structure is called borazine, borazole, or inorganic benzene. This has a cyclic conjugation. It happens to be having the condition satisfied. So, this particular compound again is conjugated, but it does not contain any carbon in it. Further, we could even have a case where we have a lone pair, we have the single bond, and we have unpaired electron. Now, this could be satisfied in something like the ether radical. We can have CH3, CH radical, O, CH2, CH3. Here, this particular radical is conjugated with the oxygen's lone pair and is satisfied and is stabilized. So, this is what we have as the few conditions in which conjugations can take place and does take place. Now, these are the few compounds where the conjugation takes place. Now, the conjugation can take place in the cyclic structure as well. Now, let us say we have the simple structure. The simplest cyclic structure is the cyclopropane. When we talk about the cyclopropane, none of the condition of conjugations are satisfied in it. All the carbon are sp3 hybridized and there is no unhybridized p orbital to take part in conjugation. But when we talk about something like cyclopropene, cyclopropene has the pi bond, but it does not have another condition being satisfied, so the electron cloud remains localized between two carbons. But if we have cyclopropenyl cation, now each of the carbon here is sp2 hybridized, while the top carbon contains an empty orbital. So here the condition of pi bond, single bond, empty orbital is satisfied. Cyclopropene is actually conjugated. Further, in this particular compound, all the atoms forming the cyclic structure, that is all the three carbon, contribute exactly one orbital towards conjugation. When all the atoms forming the ring contribute exactly one orbital towards conjugation, it is termed as cyclic or ring conjugation. So in this case, the cyclopropenyl cation is cyclic and ring conjugated. We could have cyclopropenyl anion also. When we talk about the cyclopropenyl anion, it is going to contain a lone pair. This also is ring conjugated because here the condition of the pi bond, single bond, and the lone pair is satisfied. We could have cyclopropenyl radical also. When we talk about cyclopropenyl radical, it contains an unpaired electron, and so here the condition of pi bond, single bond, unpaired electron is satisfied with cyclopropenyl radical. Now there is one more thing. We can even talk about the number of electrons taking part in cyclic conjugation. When you talk about the number of electrons taking part in the cyclic conjugation, remember the lone pair means two electrons. The pi bond also means two electrons. The empty orbital means zero electron, while the unpaired electron, quite obviously, would mean one electron. So, whenever we have to talk about the number of electrons taking part in cyclic conjugation, you just have to talk about what are the orbitals being contributed towards it and how many electrons are there. For example, in the first case, the number of electrons taking part in cyclic conjugation, which we can represent by a symbol omega. So let's say we say the number of electrons taking part in cyclic conjugation is given by the symbol omega. So in this case, the omega is equal to 2. because here we have a pi bond. We have an empty orbital, so the number of electrons taking part in cyclic conjugation is 2. In this case, the number of electrons taking part in cyclic conjugation turn out to be 4 because we have a pi bond, we have a single bond, and we have the lone pair. In this case, the last case, we have the number of electrons taking part in cyclic conjugation as 3 because we have unpaired electron, we have a pi bond. So the total number of electrons taking part in cyclic conjugation turn out to be 3. Now, when we talk about these cases, we have two formulae. One formula is called 4n plus 2 is equal to omega. And other formula is 4m is equal to omega. For each of the species, we find out the value of n and m. In first case, when we put the formula as 4n plus 2 is equal to omega, that is equal to 2, the value of n turns out to be 0. In the second case, the value of n turns out to be 1 by 2. In the third case, the value of n turns out to be 1 by 4. Then we can get the value of m. In the first case, value of m turns out to be 1 by 2. In the second case, value of m turns out to be 1. And in the third case, value of m turns out to be 3 by 4. Now, why exactly we are trying to find out the value of n and m? Now, here we need to understand a very simple concept and a very important concept, and that is called aromaticity. Aromaticity. The compounds in which the number of electrons taking part in the cyclic or the ring conjugation are given by the formula 4n plus 2, where n is a whole number or a non-negative integer, are termed as aromatic compounds. The first compound which we have, that is cyclopropenyl cation, that satisfies this particular condition, and so cyclopropenyl cation is aromatic. In the same manner, we have something called antiaromatic compound. The compounds in which the number of electrons taking part in cyclic conjugation are given by the formula 4m, where m is a natural number, that is, a positive integer, are termed as anti-aromatic compounds. Now, what we find is that they both, aromatic as well as anti-aromatic compound, are cyclic conjugated compounds. If the cyclic conjugation condition is not satisfied, then the compound cannot be aromatic or anti-aromatic. Rest of all the compounds which do not satisfy any of these conditions, they are termed as non-aromatic. Now, non-aromatic could be conjugated non-aromatic or it could be non-conjugated. Once we have said non-conjugated, it automatically becomes non-aromatic. Now, these compounds, they have different stabilities. If we have a formula, something like C6H6, this formula could represent aromatic, anti-aromatic, non-aromatic, non-aromatic conjugated, any kind of compound. Now, what we find is, if we arrange them in the order of stability, we find aromatic is the most stable, followed by conjugated, non-aromatic, followed by non-conjugated, followed by anti-aromatic. The anti-aromatic structure is the least stable. So what we find is aromatic. For example, let's say we have benzene. Benzene follows the formula C6H6 and is aromatic. It's cyclic aromatic. Then we have conjugated non-aromatic. Conjugated non-aromatic could be HC triple bond C, C, H double bond CH single bond CH double bond CH2. Now this particular structure is conjugated, but it is not aromatic simply because it is not cyclic. Then we could have something like HC triple bond C single bond CH2, CH2, C triple bond CH. Now, this particular compound is non-conjugated, and sincerely, when it is non-conjugated, automatically it becomes non-aromatic as well. Then we could have a structure like this. Here, this particular structure is anti-aromatic. As you can see, this particular compound, the square, it has two bonds, two pi bonds, which are conjugated with each other. The total number of electrons taking part in cyclic conjugation turn out to be 4, and so M value comes out to be 1. So this particular compound is conjugated, cyclic conjugated, and anti-aromatic. So that is what we have as the example. For the same formula, we could have all the kind of compounds, and this would be the stability order. Considering this aromaticity, we could have many other examples which could be aromatic, anti-aromatic, or conjugated. Now let's see, have certain examples. Let us say we have a compound, a simple cyclobutadiene. In case of cyclobutadiene, the number of electrons taking part in cyclic conjugation are 4. The M value turns out to be 1, and this compound is anti-aromatic. Now let's say we have cyclobutadiene cation. That's one of the carbon contains positive charge. This carbon which is containing the positive charge would be having an empty orbital with it. But the important thing is that one atom at any time can contribute only one orbital, whether it be a pi bond, whether it be empty orbital, whether it be a lone pair, or whether it be unpaired electron. Now in this case, already we find that the two pi bonds are conjugated with each other. Putting an empty orbital on any of the carbon is not going to make any difference, as this empty orbital will not be able to take part in conjugation. So here what we find is, again, there are two pi bonds which are conjugated with each other. It's cyclic conjugated, and the number of electrons taking part in cyclic conjugation is 4. So this compound again turns out to be anti-aromatic. Let's say we talk about cyclobutadiene anion. We put a negative charge on any of the carbon. Now, in this case, you might be tempted to say that a lone pair is there, then we have two pi bonds, so 6 electrons are taking part in cyclic conjugation. But the fact is, here again, we have only 4 electrons taking part in cyclic conjugation, as the lone pair is not going to conjugate. One carbon cannot contribute a pi bond as well as a lone pair towards conjugation. So here again, there are 4 electrons taking part in cyclic conjugation, and this again is anti-aromatic. But if we have a cyclobutadiene dication. Here we have 2 electrons taking part in cyclic conjugation. We have the empty orbital, single bond, pi bond, single bond, empty orbital. And this condition is the condition of aromaticity. So this is aromatic. Similarly, cyclobutene dianion also would turn out to be aromatic. We can have cyclopentadienyl anion. This cyclopentadienyl anion has 6 electrons taking part in cyclic conjugation, and this cyclopentadienyl anion is aromatic. Talking about the structure, like we have cyclohexadiene and cyclohexa 1,4-diene. Now, this particular compound, you might be tempted to say that there are 4 electrons taking part in conjugation, but the problem is these 4 electrons are not even conjugated. This is non-conjugated. So, of course, it can't be aromatic. This is non-conjugated, and hence it is non-aromatic. If we have cyclobuta 1,3-diene, cyclobuta 1,3-diene is conjugated, but it is not not cyclic conjugated, and therefore this is not aromatic or anti-aromatic.